incredibly fascinating world of alternating current. If you've ever looked up at a massive power line or, tuned an old school radio and wondered what exactly is happening on a fundamental physical level, well, you are in exactly the right place. Today, we're breaking down the literal architecture of our modern electrical grid in this explainer. Here's our roadmap for the journey. We've got 1. The AC power revolution. 2. Resistors in AC circuits. 3. Visualizing with phasors. 4. Inductors and capacitors. 5. The series LCR circuit. And finally, 6. The magic of resonance. Okay, section 1, the AC power revolution. Let's look at the historical battle that set the stage for electrical grids all over the world. So the man really behind the magic here is Nikola Tesla. Along with George Westinghouse, he fiercely championed alternating current, or AC power, over Thomas Edison's direct current. And you might be wondering, why did they win this epic war of the currents? Well, the biggest reason is that alternating voltage can be easily and very efficiently stepped up or stepped down by transformers. This means we can transmit electrical energy economically over huge distances without losing all that precious power to heat along the way. It was an absolute game changer. Now, to truly understand why AC is so special, we really have to contrast it with DC. While direct current flows in a single, unyielding direction, kind of like a one-way street, alternating current varies like a sine wave. It's constantly reversing its direction with time. In fact, the voltages and currents in your home right now, they're doing this exact rapid dance. But here's the catch. This constant fluctuation creates a real measurement problem. Think about it. How do you measure something that mathematically averages out to 0 over a full cycle? Because AC is constantly fluctuating, we measure it using something called the root mean square, or RMS. This gives us a steady, effective baseline to compare against DC power. So when someone says a household outlet is 220 volts, that's actually the RMS value. The actual peak voltage is much higher, hitting about 311 volts. Basically, the RMS current is the equivalent DC current that would produce the exact same average power loss. Make sense? Moving right along to section 2, resistors in AC circuits. Let's see how our very first fundamental component reacts to this alternating flow. The humble resistor has a very, let's say, straightforward personality. When you hook an AC voltage source up to a pure resistor, the voltage and the current are perfectly in sync. They hit their 0, their minimum, and their maximum values at the exact same time. We call this being in phase. And just like in a DC circuit, as this alternating current passes through, the resistor steadily dissipates electrical energy as Joule heating. It consumes power directly proportional to the square of the RMS current. No surprises there. That brings us to section 3, visualizing with phasors. Because, not every component is as perfectly well-behaved as a resistor. To keep track of components that aren't perfectly in sync, we use a brilliant visual tool called a phasor. Imagine phasors like the rotating hands of a clock, spinning counterclockwise at a specific angular speed. They perfectly illustrate the invisible timing differences in our circuits, letting us see exactly when a current is leading or lagging behind the voltage. Even though voltage and current are actually scalar quantities, using these rotating vectors gives us a surprisingly simple way to map out their shifting relationships mathematically. All right, section 4, inductors and capacitors. Let's introduce two components with very distinct and, frankly, almost stubborn personalities. Let's look at the inductor first. It's essentially just a coil of wire. But thanks to Faraday and Lenz's laws, the inductor actively resists changes in current by creating a self-induced EMF. It acts super sluggishly. This opposition to the current is called inductive reactance. And what's absolutely fascinating here is that this reactance scales up with the frequency of the current. Literally, the faster the AC current tries to change, the harder the inductor pushes back. Because it so aggressively resists change, the current through an inductor always arrives late to the party. If we look at our phasor clock, the current phasor is lagging a full quarter cycle or 90 degrees behind the voltage phasor. But here's the absolute most mind-blowing takeaway from the physics here. Despite limiting the current, the average power consumed by a pure inductor over a full cycle is exactly 0. Yeah, 0. The energy just endlessly sloshes back and forth between the power source and the inductor's magnetic field.
Now, on the flip side, we have the capacitor. When connected to an AC source, the capacitor is being alternately charged and discharged over and over. It also regulates current, an effect we call capacitive reactance. But unlike the sluggish inductor, a capacitor's reactance is inversely proportional to the frequency. This means high-frequency AC breezes right through, while low-frequency AC faces heavy opposition.
The capacitor is super eager. It charges up incredibly fast. Because of this, its current actually leads the voltage by 90 degrees. It's a quarter cycle ahead. And just like the inductor, we run into another mathematical marvel. Thanks to this 90-degree phase shift, a pure capacitor also consumes zero average net power over a complete cycle. Pretty cool, right? So let's just pause for a second and lock in this conceptual checkpoint, because it is entirely foundational. Resistors are totally in phase, and they actually consume power as heat. Inductors stubbornly lag behind the voltage by 90 degrees, but consume zero net power. And capacitors eagerly lead the voltage by 90 degrees, and they also consume zero net power. Okay, moving to section 5, the series LCR circuit. Let's see what happens when we wire all three of these characters together in a single series circuit. Now, because these components are all fiercely fighting over the timing of the current, we can't just add their resistance and reactances together with simple math. To find the total opposition to the current, which we call impedance, we have to map them out step by step. Picture this. The resistor is on the horizontal axis. The inductor points straight up. The capacitor points straight down. Because the inductor and capacitor phasors are exactly 180 degrees opposite, they actively fight and cancel each other out. To find the final impedance, we take whatever is left over from that cancellation and use Pythagorean math with the resistor to calculate the final hypotenuse. And that brings us to section 6, the magic of resonance. This is the grand finale, where these three building blocks create something truly magical for our everyday technology. Since the inductor lags by 90 degrees and the capacitor leads by 90 degrees, their reactances are in a constant, invisible tug of war. But what happens if we tune the frequency of the AC source so that those two reactants are perfectly mathematically equal? What happens when they completely cancel each other out? Well, it creates a beautiful phenomenon called resonance. When the inductive and capacitive reactances completely cancel, the circuit's overall impedance drops to its absolute minimum. It literally just becomes the value of the resistor. Because opposition is at its lowest possible point, it allows a massive, powerful spike in current amplitude. And this happens at one very specific natural frequency for any given LCR circuit, which is calculated as 1 over the square root of L times C. Now, this isn't just dry textbook math. This exact physics is literally how we communicate globally. When your car's radio antenna is sitting out there, it is being bombarded by thousands of overlapping frequencies in the air all at the exact same time. But by simply adjusting a variable capacitor in your radio's LCR circuit, you actually change its resonant frequency. The circuit acts almost like a bouncer at a club. It rejects almost all the signals trying to get in, but accepts and heavily amplifies the one specific current that perfectly matches its resonant frequency. It truly leaves you wondering, doesn't it? If a few simple components, just coils of wire and metal plates, can pluck invisible information out of thin air simply by balancing out their phase differences, what other fascinating physics are swirling around us right now, just waiting to be tuned into? Thank you so much for joining this explainer, and keep your curiosity resonating.